Welcome back to another video. In this video, I want to talk about blue noise in cycles. Let's look at an article that I wrote about it to show some examples, especially the renders, which are the most important, the result of this improvement. So the TLDR is pretty much, this is what sampling looked like at low samples. And I don't know how many samples this was, probably like 16 or 32. And this is the new version. And this is the same render time, same amount of samples, but the samples have a different pattern. And that pattern is called blue noise. So that's it. If you want to use this, just make sure you use Blender 4.4, and it's pretty much already enabled by default, so you don't really have to do anything. But the setting is found under render and then under sampling, all the way down to advanced. You got your pattern, and that is by default set to automatic, which uses blue noise, but you can set it back to classic, what it used to be, or blue noise, which is forcing it to use blue noise. I think automatic also use blue noise, but it does something different in viewport rendering. Yeah. So setting it to automatic is fine. So you don't really need to do you don't really need to do anything. You don't need to know about this necessarily, except for when you use older blend files that were created with Blender 4.3 or before, and you open them in 4.4. You can generally always open older blend files in newer versions of Blender. That is really well done with backward compatibility. But if you have saved a file in 4.3, the pattern will be set to classic. And in that case, you might want to change it to automatic to get this benefit. So let's look back at the article. Yeah, this is a day and night. I don't know how the recording will, how the screen recording will capture this, but if it doesn't show it well, you can check the link in the description to the article. But yeah, that's pretty much the setting. And I went a little bit deeper into like, why does this work and what is blue noise compared to the regular one. I think the classic one is something like white noise. It wasn't exactly white noise, but yeah. So what is that? What is this stuff? And why do you need like random sampling? So in order to get a little bit into that, what you need to know is that the samples setting in cycles, let's open that up. So we got render, our max samples. What is this setting? 1024. That's how many samples cycles takes per pixel. And what does that mean? Every pixel, the purpose of rendering is coming up when finding the color of each pixel. In order to do that, it needs to shoot out rays from your camera into your scene. And one ray that will hit something and that will create a path that you're tracing. So Cycles is called a path tracer. So it traces paths of lights through the scene. And every pixel needs more than one of those light paths generally. And every light path that it traces is called a sample. And then at the end, when you get all your samples done, every sample will end up being like a brightness and a color. And then you take the average of those, or maybe more a weighted average. And then you come up with the final color of the pixel. So the more samples you take, the better it is pretty much. But there are ways to do it more intelligently, and that is what you do with this noise pattern. So if you say, okay, I know I need to take multiple samples for every pixel, you could take all those samples exactly and shoot them out through the center of your pixel. And a pixel is pretty much a little square. So you could, from the camera, you could shoot them out through the center and then all the same direction. But then you might not get an accurate color because all the light rays will start off in the same direction. So what you can do then is shoot them out in a different direction. So if this black thing is your pixel and you know you need to take 64 samples, you can shoot all your samples out in this way. So you can, every blue dot here is a sample, and it's pretty much a ray starting off through the pixel from the camera. You could do it like this. This is a very nice distribution, but this has issues because it's too there's not enough randomness in here, and it causes like aliasing issues. So then another approach could be to use a fully random way. You just create 64 random points, and the way you create a random point is you have a random number generator that generates a number. Let's say the size of your pixel is 1, so this is 0 in X, 1 and 0 and 1 in Y. So you create a value from 0 to 1 with your random number generator for X and for Y, and that's your coordinates. That's what you get. This is the kind of pattern you get when you do that. And that's what cycles used to do. And then you end up with a render that has a noise pattern that looks like this. The problem with this is that you can see a lot of clustering, and you also see a lot of open areas. So the distribution is not that nice. So in this case, the distribution is better, but there is no randomness. So what you want is the best of both worlds, and that's what blue noise is. And blue noise looks like this. And if you render with this instead of the white noise, this is the difference. This is another example. This is one I created myself, and I created this simply by setting the samples to something low. I think it was 16 or something, or 32. And I first set it to classic. I set the pattern to classic. That's the left side. And then I set it to blue noise. And you got the right side. And again, the window is where you see the most difference. And I think that makes sense, because if you think about it, if you would shoot all your rays in the same direction for every sample, sometimes you got shaders like a diffuse shader that still add randomness to the path. Because if you hit a diffuse material, the reflection direction of the ray will be random, because it can be in any direction. But if you hit a perfectly reflective surface, the direction is pretty much determined. If you have a zero roughness, then the reflection will be exactly known. So if you shoot your rays all in the same direction, you will get the exact same result from hitting a reflective surface with a zero roughness. So that's when this stuff is problematic, because all these four clustered samples will shoot rays in the same direction, and they will end up being the same thing. So they don't really add much information to your render. Whereas this is more distributed. So that's what you can see in the window, where the window has probably a very low roughness, maybe even zero. And then you clearly see the difference. So yeah, that is blue noise. And then I got curious about how do you make this? Like, how do you create blue noise? Because this pattern is pretty easy to create. You just put the points in a nice grid. This one is easy because you just use a random number generator and you create your random coordinates. But then you get the clusters issue. Then you got blue noise. How do you create this? And there are multiple algorithms. There's a lot of research done on how to create blue noise patterns, because blue noise is very useful for other things other than rendering. You can imagine if you need to put grass on some area in your scene, in a 3D scene. And you have a particle system that spawns the grass. If you use a completely random particle system, you get a lot of open patches, open spots where the grass doesn't cover the area properly. So then you need to increase the point count, and that slows down everything, slows down rendering. So if you have a better distribution, you can get away with less particles and still get the proper coverage. So that's where blue noise is also very useful. So yeah, how do you create this? And I found an interesting, pretty elegant algorithm that's called Mitchell's Best Candidate algorithm. And the way it works is you start off with white noise. You just start off with the first point just being completely randomly generated. And then for the second point, you first create a bunch of candidates, and then you select the best one. And the candidates are generated in the same way white noise is generated, completely random. But then so for example, for the second point, you might create 2 candidates, which are completely random. But then you pick the one that's the furthest away from any other point. That is what's called the best one. And then you discard the rest, and that's what you get. And then for the third point, you create 3 candidates, and then you pick one. And the key is to keep increasing the number of candidates as the amount of points grows. And that's also why it's not a very fast algorithm. It doesn't scale very well. So, but it's still a very nice and simple idea. Like, you just create some random points, and then you only pick the best one that's the furthest away from any other point. And that gives you a really nice distribution. And that's how I created this image. And because I implemented this in geometry nodes, and we can look into that. Oh yeah, I made a little animation of how the algorithm works. So the first point is just random. We just pick a random point, and then it becomes blue because that is our existing set of points. They are blue. And then we pick 2 points, and it's a bit dark. We pick a point here and here, and then we pick the one, we only want to pick one that's the furthest away from any other point. So we only have 1 point. So this one is clearly the furthest away. So that's the one we pick, becomes green, and the other one will be discarded. Now for the third point, we create 3 candidates. So 1, 2, 3. And then we pick the one that's the furthest away from the rest, the one that's clearly this one. So that one will be green. We remove the other ones, and this one is added to our set of points. And then it keeps going like that. 4 candidates, 5 candidates, and so on. And you end up with a nice blue noise pattern. So if you're familiar with geometry nodes, there is a way to distribute points for things like particle systems in a better way than purely random, and that's the Poisson Disk setting. And this pattern generates a very similar pattern to blue noise. So that's interesting to know. You can use that as well, and it's a bit faster, I think. For if you need to create a couple thousand points, this might be faster. But you cannot say how many points you want. You can only work with a density and a distance. And if you increase the distance, the amount of points will go down, because that's the minimum distance that the points need to be separated by. So yeah, that's a different way to create the same kind of pattern. And that creates this pattern. But yeah, let's look at how I created this noise pattern in geometry nodes, because that might be interesting. So let's look at regular. Okay, I have here this noise object. Let's look at, this is just the regular sampling, and yeah, it's a little bit, I might have overcomplicated this, but I wanted to have a nice square amount of points. So I take the square root, and then I square it again. I forgot where I do that, but yeah. pretty much if you choose a non-square point, it just takes the closest rounded down square root, where 64 is a nice square root. The one below that is 49. So this is 49 points, as you can see here. And then when you go below that, it becomes 36 points. So yeah, this is, I'm not going to go into this. This is just a simple, the key here is using divide floor. If I can find it. Yeah, divide floor for the X and modulo for the Y of the index. And I divide by the square root. So if I have 64 points, I divide by 8 and I do divide floor and I take the modulo 8. And that's how I get my X and Y. And yeah, but that's not what we're here for. This is the white noise one. This is very simple. This is just, I create a bunch of points with a count and a radius. And I choose a random value from -1 to 1 in X and Y. And that's what you get. And you get this clustering problem. And if you think this is just a coincidence that there's clustering, you can change the seed and you get a totally different one, but it's always going to be clustering and there's always going to be empty spots. That's just the nature of this pattern. So yeah, that's a problematic pattern for many reasons. So yeah, but it's very simple. It's white noise. And then we have our blue noise, and that one looks really nice. And it's a lot more complicated. So what I do is, instead of creating a bunch of points, I create only one point at a time, and I use a repeat zone to iterate, and the amount of iterations is the amount of points plus 1. But we set the count to 64 and we get exactly 64 points. And that's how it's generated. And this is not that complicated. It's pretty much, we iterate how many points we want. We keep repeating that. And we have this group called blue noise point, and this adds a single point every iteration. So we take our existing points and we plug that into original points. And then we take the number of candidates we want, and that's the iterations times 4. And that's why we have to add 1. Maybe we can actually add this one in. Maybe we can add it here instead. 56. Yeah, that's bad. That makes more sense. So the count is the iterations, and we have the iterations start from 0, so we add 1. So the first time we run this, we got 1. We multiply it by 4. We can multiply this by an arbitrary constant. 4 is a nice balance between the higher you set this, the slower the algorithm will be. But yeah, anyway, the way it works is we take our existing points, plug it into original points, and then we take how many candidates we want. And then we create random candidates and we pick the best one. And that 1 point comes out here. We join it together with the rest. And that's going to be our points for the next round. And I also, for visualization purposes, I wanted to see the discarded points as well. But yeah, that's pretty much how it works. And then the most complicated stuff is inside of this group. So here, I'm not going to fully walk you through this, but if you're interested in how this works, we start with the candidate count and we create points, how many candidates we want, and the position is going to be randomized. So this is a random number generator, the same way we created the white noise. We just create random points. That's all this does. And then here we take our original points and we're going to sample a certain point, which is the nearest to our random value. And this random value is, we have multiple random values here. That's the amount of candidates. So this is kind of a mind bender. Like we have the number of candidates random values, and then we have a number of original points. And So from all those original points, it picks the nearest to our random value. And it does that for every random value that we have. And then we take that index and we sample it and we take the position of that nearest point. And then we get the distance from the random value to our nearest point. And that's the value we use to sort our elements. And here I kind of negate the value because I want to flip the order of the sort. So we sort our candidates by how far they are away from their closest original point. And then we throw away everything except for the 0th index. And because it's sorted, it will pick the best one. And here we do the opposite because we want to see the discarded points. Hope that makes sense. But yeah, that's pretty much what it does. And I didn't want to go into setting this up from scratch in the video because then it would be like a 2-hour video. So yeah, that's how we pick a blue noise point, and then we iterate that, we repeat that. So it was already kind of a double loop inside of this, and then we have another loop. So it doesn't scale very well, this algorithm. But yeah, that's pretty much how it works. And then you get this, and yeah, the animation visualizes this algorithm quite well, but we can also do it like this. So I take the discarded points and I set the radius really low so you can see the difference. So the first time around, we pick 4 points and then we pick a random one because there's no points to compare with. So we have 4 candidates, we pick one and we discard the rest. So the second one, they're gone. So to get the second point, we pick 8 candidates. Why 8? Because we're at the second point and our multiply is set to 4. We could also set it to 1 to kind of keep it a little bit less crowded. So we have 1 point. Then we pick our second point. We get 2 candidates, these 2. And then we pick the best one. That's the one that's furthest away to reduce that clustering effect. And then we discard this one. Then we pick our third point. So we have 3 candidates, 1, 2, 3. And again, we pick the one that's the furthest away from the rest. And that's kind of how it works. And you can see those randomly generated points. There are a bunch of them that are too close to other points. And they are discarded because we only pick the one that's furthest away. And if we start to get an area that has no points, maybe like this area, the chance becomes pretty high that one of the candidates will be in this area. And if it is in an area that's not occupied by many points, it's very likely that it will be selected as the best point. So soon enough, we'll probably, yeah, there we go. We have a point now in this kind of empty area. And now this area is a bit empty, so that's probably, yeah, there we go. Well, we will soon get another point. And yeah, that's how it works. And yeah, I can make this blend file available if people are interested to play with this. But here we can hide those candidates again. And that's pretty much how it works. And then we have a fourth one called the Poisson Disk. And I still have a count, but as you can see, the count is set to 64, but we only have 33 points because I tried to come up with a density based on the count and the area, but then you still have to deal with the minimum distance, which kind of, yeah, if you set the minimum distance to 0, the count is what we have here. Because I just pretty much calculate the area of our, the size of our square, which is 2 by 2. And then I take the count and I divide it by that area, which gets us a density. And I plug it into the density. Yeah. But then once we start increasing this distance, and I think if you set the distance to 0, you get pretty much a white noise pattern. And then what the Poisson disk does is it just takes this white noise and it removes points that are too close. So that does solve the issue of clusters getting removed. but it doesn't solve the issue of the open patches. You still need more points to get rid of those patches. So yeah, it's a little bit different. And this one is only for 2D because we need to have a mesh to put the points on. We put the points on the face of this mesh that looks like this. So yeah, that's a different way of creating this pattern. And if we look back at the blue noise, oh, this is the animation version. Let's look at the regular blue noise, and we can do this in 3 dimensions as well. That's the final thing I want to show. Like here, I set the minimum from -1 in X and Y, but the Z I don't use. I keep them at 0, but we could set this to -1 as well and create a little bit of a cube. And this will still have the properties because the distance function works in 3 dimensions as well. And that's the only thing we need to sort our points. Here we use this distance, which is actually a waste of resources a little bit if you only need 2 dimensions, because this distance calculates the distance in 3 dimensions. And you could do this manually with math nodes, but I thought the distance is more elegant because it's only 1 node, and it's probably faster because it's implemented in C or C++ in Blender internally. So yeah, I just went for the distance. The distance node in the vector math nodes. So yeah, that is blue noise. I hope that was interesting. I am considering doing a more geometry nodes focused tutorial about how to set up the blue noise from scratch and actually use it for something useful, if there's interest for that. But yeah, for now, I'll keep it at this. Blue noise is being used by cycles to make your renders look better, going from this to this. So, hope that was helpful. Hope you learned something about noise patterns, and I'll see you in the next one.